Let's now discuss electrochemical cells that are under non-standard conditions. Up to this point, everything that we've talked about has been under standard conditions, right? You've seen E naught, E naught cell, delta G naught, and I'll remind you that that would require us to have 1 molar concentrations for all of the solutes in aqueous solutions or 1 atm pressures for gases. But very often we're preparing a system that is not at standard conditions. We're not always using 1 molar concentrations for everything, and so we're not always at standard conditions. And we'll need to think about how we can describe a cell that is using non-standard concentrations. To do that, it's helpful to remember how we get the value of delta G non-standard from the standard value of delta G. Previously, we've seen the equation delta G non-standard equals the delta G at standard conditions plus RT times the natural log of Q. And now what we can do is manipulate this equation to help us to see how the cell potential at non-standard conditions relates to the cell potential at standard conditions. We'll do that by substituting in that delta G standard is equal to negative NF E naught for the cell. And as a result, we could also say that delta G non-standard is equal to negative NF E non-standard for the cell. So both of these can be substituted into our delta G equation. And when you do that, you get negative NF E non-standard for the cell equals negative NF E standard for the cell plus RT ln of Q. And to solve for E non-standard, you could divide both sides by negative NF. And when you do that, you get E cell equals E standard for the cell minus RT over NF ln of Q. This equation is called the Nernst equation, named after Walter Nernst, who came up with it. And I don't know, it's kind of crazy he got an equation named after him for just doing this little 2-step proof. But back in those days, when there was a lot of low-hanging fruit, and so it was pretty easy to get things named after you. Not so easy these days, but I'd rather be living in the 2000s than to be living in the 18 or 1900s, that's for sure. Let's get some practice using this equation. So we're going to take a look at conceptual questions and also some calculation-based questions. Here we're going to study this reaction, zinc plus 2Ag plus goes to zinc 2 plus 2Ag solid. And we're going to start under standard conditions with 1 molar concentrations of the Ag plus and the zinc 2 plus. Then what we're going to do is increase the concentration of zinc 2 plus to 2 molar, and that will put us at a non-standard condition. Let's think about what that's going to do to this cell potential. Is it going to cause the cell potential to increase? Is it going to cause it to decrease, or will there be no change? Take a moment to think about that, and then we'll talk about the answer. Having given you some time to think this over, let's talk about the answer and talk about a couple different ways that you can approach this problem to get the answer. One way that you can do this is by using Le Chatelier's principle. So we have the reaction written out here, and in this problem we were told that we increase the concentration of zinc 2 plus. And then Le Chatelier's principle says that if you increase the amount of a product, then that will cause the reaction to shift to the left. Now, how can we relate this to cell potential? If the reaction is shifting to the left, what does that mean about the spontaneity of the reaction? If it's shifting to the left, then that means that the reaction is less spontaneous. And I'll remind you that the cell potential is the driving force for the chemical reaction to occur, right? That's like the driving force for the spontaneity of the reaction. And so if the reaction is less spontaneous, there will be less of that driving force, and so there should be a lower cell potential. So that's going to decrease the cell potential. That's one way that we can analyze the answer. Another way that we can get the answer is by analyzing the Nernst equation. All right, so we can write the Nernst equation. E cell equals E naught cell minus RT over NF ln of Q, and then we'll write the Q expression out for this reaction. We do products over reactants raised to their stoichiometric coefficients. For the product side of the equation, we have zinc 2 plus, and coefficient is 1, so raise it to the first power. We also have Ag solid, but solids don't count, so don't put that in there. Divide by reactants. For the reactants, we have zinc solid, that doesn't count, but then we have Ag plus aqueous, that does count. Ag plus, the coefficient is 2, so make sure to square it. Now, in this problem, what we're doing is increasing the concentration of zinc 2 plus. So if we increase zinc 2 plus, then that's going to make the natural log bigger, right? That's going to make this whole term bigger. Now, we have a negative sign out in front. So what you're going to do is you're going to be subtracting a bigger number. And so if you subtract a bigger number from E naught cell, that will make E cell smaller. So that's another way that you can arrive at the answer from using the Nernst equation, or you could also arrive at the answer from thinking about Le Chatelier's principle. Let's now do a calculation. So we're going to consider this same reaction, zinc plus 2Ag plus going to zinc 2 plus 2Ag, and we're asked to calculate the cell potential at 298 Kelvin when the concentration of Ag plus is 0.1 molar and the concentration of zinc 2 plus is 1 molar. We're given the standard reduction potentials for Ag plus and zinc 2 plus, and let's think about how we can rearrange them to get the reaction that the problem is asking for. The problem requires zinc solid to be on the left-hand side of the equation, and so we have to reverse the zinc half reaction. The Ag plus should be on the left-hand side of the equation. It already is, and so we don't have to do anything to the Ag plus half reaction. So we'll go over to the next slide, and we'll rewrite the reactions written in the proper way. All right, having written the reactions in the appropriate way, the next thing for us to do is to balance the electrons. So we'll have to multiply the silver reaction by 2, but remember that the value of E naught stays the same. That is an intrinsic property of the system. So when you go ahead and multiply that all out, you're going to get 2Ag plus zinc going to zinc 2 plus 2Ag, and the full cell potential at standard conditions comes out to 1.56 volts. All right, so we have that part so far. That would be what the cell potential would be if everything was at 1 molar concentration. But it's not. We're told in this problem 0.1 molar concentration of Ag plus and 1 molar concentration of zinc 2 plus. So now we're going to use the Nernst equation to convert the standard cell potential into a non-standard cell potential. Let's go about doing that. So next, we'll say that E for the cell is equal to the standard cell potential of 1.56 volts minus R. Now a volt is a joule per coulomb, so R should be the one that has joules, 8.314. T is 298 Kelvin, that's what the problem told us, over N. N represents the number of moles of electrons, and in this reaction, the coefficient of E minus is 2, and so N is equal to 2. We'll go ahead and put that in here. And I'm going to say a word about the units on this in a moment, because there is an important thing to take note of about that. And then F is 96,485 coulombs per mole of electrons. And we multiply that by the natural log of Q. Now Q for this reaction is the concentration of zinc 2 plus over the concentration of Ag plus squared. So we'll plug in the numbers that the problem has given us here. So we were told that for zinc 2 plus, it was 1 molar. And we were told that for Ag plus, it was 0.1 molar. And that gets squared because the coefficient is 2. All right, now the units. So what we'll do here is say that we get Kelvin to cancel out, and the moles of electrons cancel out, and what we are left with is a unit of moles that we have from R, and so it's a little bit hard to see how that unit gets canceled out. What I'll tell you is that the units for N, the number of moles of electrons, are a little bit more than just moles of electrons, because when you use a stoichiometric coefficient, yes, that tells you moles, but that also tells you moles per every mole of chemical reactions that you do. Now, that is implied in the vast majority of calculations that we do. We would typically just say 2 moles of electrons, but that is implied that it is 2 moles of electrons per every mole of chemical reactions that you do. You'd have to do a mole of reactions to make 1 mole of zinc 2 plus, or to use 2 moles of electrons. So it's implied that it's 2 moles of electrons per every mole of reactions. We don't often write it, but I am going to show it here so that now we can see how the units properly cancel out. The moles of electrons go away, and then the moles, the per mole of reactions cancels the per mole from R. That leaves us with units of joules per coulomb, and that's the same thing as volts. When you go to calculate this out, you will find that the cell potential at the non-standard concentration specified in this problem is 1.55 joules per coulomb, or that's 1.55 volts. We see that the cell potential has decreased. It's not by much, but it is by an important amount. And we'll see problems where there will be a much larger difference that will come into play as we get even more diverging concentrations for the reactant in the product.